podcast is brought to you by LMU Munich.
The first thing I wanted to do today was to thank the organizers for all of the hard work they've been doing, and also wanted to thank them for letting me speak here at this conference and tell you a little bit about what I've been thinking and the work we've been doing in this past year. So what I've been talking about today is path integrals in 3D gravity, and I'll be giving two talks in one, so I'll be going a little bit quick. So I'm going to do computations of these path integrals for theories basically just for general relativity, and I'll do it both in ADS and DS. And it's always good to acknowledge your collaborators. So this talk, it's basically based on these 5 papers. I won't have time to go into all the technical details of the computations. I'll just flash how we proceeded. But if you have any questions, please, I'll be happy to discuss any of the details of the computation. And also this stage is really, really big. So, okay, so let's start. That looks funny. Okay, yeah. So one way you can think, one motivation we had was the following. So in ADS-CFT basically provides for us a definition of quantum gravity. So you can just state the question, part of our work as like, well, if we have a definition of quantum gravity, is there a CFT for which the spectrum of that CFT matches with the spectrum of just pure gravity, just metric degrees of freedom? And there's 2 comments regarding this question. One, it's very difficult. It's very difficult to construct a CFT that just has a gravity spectrum. But I'll also show you that if you force the issue, you can succeed. But unfortunately, my guess is that a lot of you will not be happy with the result because it looks a little bit silly. And I'll tell you the silly part of it. But in general, the kind of questions we're thinking about and our goals is roughly just understanding the integration contour of general relativity. So how to define a gravitational path integral, which contributions should go in, how you organize it, and identify the physical states. And I also want to highlight that all the computations I'll be discussing here do not rely on supersymmetry or extremality. They rely on other symmetries and conformal symmetries, well, some of the time. But I'm not doing any string theory or anything that involves supersymmetry. So it's just an honest computation of the path integral of 3D gravity. So I should write down, this is the focus of this talk. So basically, I'll spend the next 20 minutes or so just computing this object. An integral over metrics weighted by their action. So it's a partition function of the sum of the geometries. I'll include both perturbative and non-perturbative contributions. And this is going to be an exact formula. I'll be powerful enough to compute all of the corrections and just tell you exactly what this function is. And again, just to stress, I'll be focusing just on pure gravity, a theory that has only metric degrees of freedom. Now, first objection is that this is probably one of the most poorly defined quantities ever. Like, okay, so what is a gravitational path integral? So the outline of the talk, basically what I have to do first is tell you how am I going to organize this function. Okay, so how am I going to organize the integration contour? And for that, I need to say a little bit about the framework and the assumptions. And then I'll go and talk about the 2 computations we did, the one for ADS gravity and the one for de Sitter gravity. Now, when I'm doing the computation in ADS, what I'll have in mind is that I'll be computing the path integral, the partition function at finite temperature, and I'll be trying to see if I can write it as a trace over a Hilbert space, okay? So I'll be trying to see if this equality is true. And I can tell you right away, this is not always true. Not for any theory that you throw to me on this side, I'll be able to write it as a trace. In de Sitter, as we heard yesterday, we're a little bit confused about, well, me personally, I'm deeply confused about what to do in de Sitter gravity. But still, I'll compute the gravitational path integral. And we'll get some interesting results there. And I think it provides a very sharp and concrete computation, and we can start talking about what are the features of de Sitter gravity and how different it is from ADS. So it doesn't just simply map from one side to the other. And also just to highlight again, these two quantities will be computed exactly. Now, this is an old topic. It's nothing new. So I should tell you what is new here. Why am I going again and revisiting the topic of 3D gravity? So there's 2 points that are new here. First is that I'll construct the most simple example of holography. I'll construct the gravity dual of the Ising model, the two-dimensional Ising model. And is that I'll be very precise about how non-perturbative effects affect de Sitter gravity. And in my mind, what I've learned from this exercise is that I think pure gravity is just not a good quantum theory by itself. That in order to make pure gravity a good theory, you need to embed it in something bigger. But now, as I already advertised, I made some assumptions in constructing this. So of course you can take the point of view that some of my assumptions were wrong, and okay, maybe if you modify my assumptions, you might get a positive result. But this is my strong conclusion out of this computations. And for those of you that want to take a nap, now you can take a nap and wake up in whatever time I have left. Okay, so very quickly, so this is the theory I'll be studying with either negative or positive cosmological constant. The coupling that is relevant here is, for both of these cases, is the ratio of the curvature of LADS or DS, in either case, divided by G Newton. It's a dimensional coupling that I'll call K throughout the talk. Okay? And there's two features that we already heard this morning about 3D gravity, and it's the fact that there's no gravitational waves, there's no local degrees of freedom, which makes it really easy to, it makes it easier to understand what are the non-trivial diffeomorphisms, and I have also a classification of smooth manifolds. So these two features here is why I actually can make sense of this path integral, and I can write something and we can have some educated discussion about what's going on. So, okay, so what are my assumptions? So here's where you start complaining. So in this path integral here, I need to tell you basically how am I going to set it up and how I'm going to break down this integral over metrics. So there's three basic assumptions that I'll make. Number one, we believe that a gravitational path integral should include a sum over topologies. So in general, any gravitational path integral you might write should be organized in a way that I have a sum over the relevant three topologies, and for each of those topologies, I sum over all the appropriate metric contributions. So this is my first assumption. It includes a sum over topologies. The second assumption is slightly a little bit stronger. So I'm assuming that the gravitational path integral always admits a saddle point approximation. So I can always organize also the gravitational path integral as a sum over instantons, the classical solutions, and around each of those instantons I have some, in principle, infinite series of corrections. And the statement is that if you're powerful enough to compute all the classical, identify all the instantons and compute this infinite series over here, you'll have an exact formula for what the gravitational path integral is. Okay? And further, the third assumption, slightly even stronger, is that within this classical solutions, I'll only include smooth manifolds. Okay? Good? No? You should not? Yeah. Okay. So let's dig in. So let's look at the case of ADS. So the first thing I should do in ADS is construct the classical phase space. So what are the relevant solutions that I have in the theory? So they fall into two classifications, well, two families. So basically I have the boundary gravitons and I have the black holes. So despite the fact that there's no local degrees of freedom, there's still interesting states in the theory. And some of the properties that they have is basically that these are the, well, in ADS3, everything obviously is just locally ADS3, but they have the feature that these are the solutions, or the diffeomorphisms that act non-trivially on the boundary of ADS. And so they carry a finite charge. And for example, here in this column here in the boundary gravitons, which correspond to the metric fluctuations, there's a nice aspect of these states, and it's that they form the symmetry group that labels them as the Virasoro group, and it's basically, if you exponentiate this group, what you get is a group of diffeomorphisms of the circle. So for example, quantizing the classical phase space of boundary gravitons is equivalent to quantizing diff S1. And okay, good. So let's start organizing this path integral. So what I want to do here is compute the path integral where the boundary of the space-time is a torus. Hence, the path integral will depend on the complex structure that labels that torus. That's the same as the finite temperature partition function where the imaginary part of tau is the temperature and the real part of tau is the angular potential. So thermal ADS is basically just a solid torus. And the basic observation here is that to get all the other black hole solutions in the theory, you just act by a modular transformation on your complex structure tau. So if I grab thermal ADS as my vacuum solution, all the other black hole solutions in the theory are just obtained by by acting with SL2C on the complex structure. And so my path integral can be organized as a sum over elements over SL2C with some seed solution right here. So this is also not new. This was a statement that was made more than 10 years ago. And sums of this type in the gravitational language are called the black hole fairy tales. And they encapsulate basically my sum over topology. So here I'm making reference to my number one assumption that it includes a sum over topology. So if you see this in ADS3 gravity, you say you have a sum over topologies. Now this function here, C vacuum, includes all the metric fluctuations. And it's basically determined by the representations of the Virasoro group. The nice feature about this is that when I write the partition function in this way, it's very obvious as well that it's modular invariant. So it does not depend on some specific choice of parametrization of the torus. Now, the other thing I should highlight is this little thing here. So if you notice, I'm not summing over all the elements of SL2C. You just sum over those elements that don't generate a new topology. Some of them will actually not change this function, and they don't give rise to something new in the bulk. So you have to be a little bit careful about what is the exact group that you're summing over here. So keep this in mind. Good. Now comes the stronger assumption. So I presented to you some very general form of what a path integral in ADS gravity should look like. And my assumption in this section is that this structure, this organization of the path integral, is true for any value of the coupling of the central charge. So that the relevant phase space that I should quantize for any value of k should be the classical phase space that I initially described. Okay? And it's an assumption. I can't prove it, but it's an assumption that we'll make in order to do some progress. So, okay. So I'm going to do now gravity at strong coupling. But the thing that you should ask me is, why didn't you just do gravity at weak coupling? And the answer is, well, this was already considered, it was already studied. In particular, there's two very nice papers that did the analysis. And what happens in general, like with the same basic assumptions that we're making here, is that in general, this gravitational path integral is not equal to a trace over a Hilbert space. So the Hamiltonian is not bounded, basically the Hamiltonian is not bounded from below. And they obtain a negative result here in this situation. So yeah, in the case where you have a semi-classical approximation, it seems to be the case that the path integral, even though you can compute it and you can evaluate it, it doesn't have a nice interpretation. So let's look at what happens when the coupling is small, in particular the central charge is less than 1. So the few things that you have to be aware of if you go to strong coupling are the following. First, there's no semi-classical approximation. So I have to be able to compute this thing entirely. There's no thing as small perturbative corrections. And so if I compute the path integral, I have to include all contributions at one soup. And the other feature that it's very interesting when you take C less than 1 is that you see explicitly that there appears a lot of null states in the Fock space of metric excitation. So when you proceed to quantize the classical phase space, it's very different if you take C bigger than 1 or C less than 1. It's basically due to the representations of the Virasoro group. So when I write down this path integral for C less than 1, I see that here my metric fluctuations that were determined by the representations of the Virasoro group are only unitary for these values of the central charge. And this is the same result that you see in the minimal model construction in the CFT side. And the other thing that happens here is that this group, gamma C, that I wrote down, is much, much bigger. So the number of topologies that contribute in this sum are basically finite. So you have only a finite sum over topologies. So, and the strongly coupled regime, a lot of states are disappearing from your classical phase space. So I should go through this a little bit more quickly. So in my search of a CFT that has a gravity spectrum, so basically I want to see if this thing can be cast in this way, there's two basic things that I'll be looking for. One is that all the coefficients in my gravitational path integral should be positive integers, and also it should be an extremal CFT. So what do I mean by that extremal CFT? There should be a gap in the spectrum of size at least C over 24. So this is the typical sort of, I'm plotting the energies basically here that I have ADS, and then I have a continuous of solutions up there. And in general, extremal CFTs are very hard to construct, so that's why okay. But the advantage that I have here when C is less than 1 is that I have a complete classifications of CFTs. So the search is very systematic. So I know all the unitary CFTs that are available, so just go and do it. And in particular, there's two CFTs that are interesting. The Ising model, so just spin up and down on a lattice, and the tricritical Ising model. And they correspond, they're inside the Virasoro minimal model classification. And the nice feature that these two CFTs have is that they're both extremal. So if you look at the primary operators in this CFT, they all satisfy the property that their conformal weights is bigger than C over 24. So they're extremal CFTs. And you can compute their partition function, and you now can proceed to compare to the gravitational result. And it works. The gravitational path integral is equal to the path integral of the Ising model when the central charge is 1/2, and it's equal to the tricritical Ising model when the central charge is 7/10. But don't get excited. It doesn't work any other time. So you can go then through the rest of the list of the minimal model classification, and this will never again be true that the gravitational path integral is equal to the CFT partition function. And there's two reasons why this is happening. Well, because these two examples, the Ising and the tricritical Ising, were the only extremal CFTs within this classification. And also there were the unique theories, the unique CFTs at those values of the central charge, so it better worked. But okay. So that's the ADS story. Now let's go very quickly through the de Sitter story. So in the de Sitter side, we're a little bit more confused about what exactly we should compute. So there's basically two options. So this is just a Penrose diagram of de Sitter. So one thing you can compute is you can compute the wave function as defined at future infinity, and this will depend on whatever boundary metric you put up here. This is something that will hopefully appear soon. But the other thing that you can compute is that you can take the point of view of the observer on the static patch and compute the Euclidean path integral with respect to the static patch observer. And so let me focus a little bit more on this computation right here. So the basic observation is that, okay, so you have in Lorentzian signature, this is a metric for de Sitter, and Euclidean signature, you just take T to IT, this is the metric, and your second observation is that you want this metric to be regular at the horizon, and so you say, oh, well, this is the metric of the 3-sphere where time gets periodically identified. But what we observe, it's a very simple observation, is that this is not the only identification that makes the horizon smooth. There are other identifications that will also make this metric smooth, and they basically correspond to length spaces. These are quotients of the three-sphere, and here P and Q are co-prime integers. So it's as equally valid as say that the Euclidean version of de Sitter is a three-sphere, or to say that it's a length space, okay? So you should be treating these manifolds kind of democratically. And so again, my observer is going to construct their classical phase space. There will be basically the quotients of the spheres that will correspond to different topologies, and I'll also have metric fluctuations. And in this setup, we again organized the sum in a saddle point approximation, and we identified all the classical solutions and computed all loop corrections. So some comments about this computation. It was very handy in this case for de Sitter to exploit the similarities between gravity and transaminance theory. They're not the same, but it's very useful in order to compute the perturbative corrections, all these metric fluctuations. So this basically, exploiting this relationship is what allowed us to compute an exact formula for the path integral in de Sitter space. Now, the sum resembled a lot the ADS sum. There was also a sum over SL2C, and that's what got us excited, that we thought that maybe the story was going to be a little bit similar, but actually it's not. So in this case, if you carry out the computation, if you sum over all of your saddles, well, in general, these sums are divergent. You have to regulate them. And in ADS, you can regulate that divergence, but in de Sitter, you can't. You get a term in your path integral that is proportional to the Riemann zeta function of 1, and this just has a divergence, like it has a pole. So it's actually not that similar to the ADS story. I can't even make sense of this sum. I can't even formally define, like, I just get a big fat infinity when I compute it. And it's independent of the coupling. So the other thing we were hoping is that it depended on the and the de Sitter radius to say that, okay, maybe the sum is only well defined for certain values of the cosmological constant, but that's not even true. So, I'm more deeply confused. So the other comment I should make is that if you compute this wave function at future infinities, we're also seeing similar problems. So if you decide that this was not the correct observable, the other observable that I propose also has some bad features. So I should end my conclusions. So what did we learn out of this exercise? So in the ADS computation, we gave a definition of what a sum over geometries is, and we noticed basically how hard it was to make it have a nice CFT interpretation, identified it with a trace over some appropriate Hilbert space. But we got a positive result, and it corresponded to basically, in our minds, the simplest example of ADS CFT. So for us, in some sense, this tells us that holography kind of works. Like the initial example was n equals 4 Sabrina-Mills, that is a very complicated CFT. But at the same time, the gravity, the Ising model is the simplest CFT, but it also has some metric interpretation. So it's sort of cute in my mind. And what is also exciting, that even though it's at a very strong coupling and a fixed value of the central charge, we finally managed to have a unitary result for a sum over geometries. So in some sense, we made it work. We had to go to very extreme limits. It shows us how much we have to push the issue to make gravity a consistent theory, and how many degrees of freedom we had to remove in order to make sense of such path integral. In de Sitter, I want to highlight that it's possible in three-dimensional gravity to account for all perturbative and non-perturbative effects. So I think it's a good playground just to explore what are the issues about de Sitter quantum gravity. And that's what we started doing. And so I think in this setup, you can start thinking about, well, what happens if I modify my initial assumptions? So those 3 assumptions that I gave at the beginning. So you can think about maybe, okay, what if you include now manifolds that have singularities, or I don't know. You can be creative. You're all very smart people. But you have a lot of control of what are the ingredients that go in and kind of test if our conclusions are correct or not. And if our assumptions were good, basically the result is that the sum of the geometries is just nonsense in the Sitter space. You just get crap. So thank you very much.
So in the de Sitter case, what was the sum over topologies that you did?
So in particular, the part that we did very explicitly was the sum over lens spaces. So each of the lens spaces it's a different topology.
So you're calculating, there's no boundary.
No, there's no boundary. So it's a sum over compact manifolds. Yes, yeah. So you can interpret it like as the norm of the Hartle-Hawking state, or, well, okay, but yeah. I mean, just summing over all compact manifolds and Euclidean de Sitter gravity.
You could have considered imitating the other calculation by fixing a boundary and trying to sum over things with that boundary.
Right, but that will be fixing the boundary at future infinity, you mean? Right, so yeah, we're also carrying out that computation, and again, you get these infinities floating, like the wave function is not, you can't regulate it, so yes, yeah, so there's different computations you can do.
In your calculation of the Ising model, you got a factor of 8 in the, why
yes.
is that?
Well, okay, so in the paper, well, yeah, when we were carrying out the computations, yes, there's an 8 and there's a 48 for the tri-critical. We took that as a measure, sort of that we were not specific about the normalization of the measure factor. And so we're taking as part of the definition of the measure of the gravitational path integral. But I think, okay, so that was just the explanation we gave, but I think this is something you can test, because the only thing we computed was the partition function for the torus. And if you decide then to, for example, compute the partition function in other the Riemann surfaces, it should be the case that when you pinch one of those surfaces, that you get always the same 8 floating around. This measure that we didn't define is consistent for all of the observables that you can imagine. So we just computed the spectrum, but then everything else in the theories in both sides has to match. So yeah, but it's a good question. The 8 is something that needs to be sorted out.